Question 1. The performance metrics show a consistent pattern of sediment leaving the construction site and entering the adjacent waterway, despite the presence of a Stormwater Pollution Prevention Plan, SWPP. As a certified erosion, sediment and stormwater inspector operating under the U.S. Clean Water Act, what is the most appropriate immediate course of action to address this ongoing noncompliance? Option A. Issue a formal notice of violation, detailing the specific instances of sediment discharge, referencing the relevant sections of the Clean Water Act and the site's SWPP, and requiring the implementation of immediate corrective actions with a specified timeline for follow-up inspection. Option B. Advise the site operator to temporarily halt all land-disturbing activities until additional erosion and sediment control measures can be installed, without issuing formal documentation of the current violation. Option C. Document the sediment discharge but defer further action, assuming the site operator will self-correct the issue given the ongoing nature of the construction project. Option D. Immediately assess the potential fines associated with the observed sediment discharges and issue a penalty notice to the site operator, citing the Clean Water Act violations. Correct answer is A. Issue a formal notice of violation, detailing the specific instances of sediment discharge, referencing the relevant sections of the Clean Water Act and the site's SWPP, and requiring the implementation of immediate corrective actions with a specified timeline for follow-up inspection. Explanation. This scenario presents a common implementation challenge for certified erosion, sediment and stormwater inspectors, SESI, operating under the U.S. Clean Water Act (CWA) and its associated National Pollutant Discharge Elimination System (NPDES) program. The challenge lies in balancing the need for effective stormwater management with the practical realities of construction site operations and the potential for unforeseen circumstances. Inspectors must interpret and apply complex regulations to dynamic environments, requiring a deep understanding of both the letter and the spirit of the law. The correct approach represents best professional practice because it prioritizes compliance with the CWA's stormwater discharge regulations by directly addressing the identified noncompliance. It involves a systematic process of documentation, communication, and enforcement, which are fundamental to the NPDES program's objective of protecting water quality. This approach ensures that the permittee is aware of the deficiencies, has an opportunity to correct them, and that appropriate measures are taken to prevent further pollution. This aligns with the SESI role as a guardian of environmental regulations and public health. An incorrect approach that focuses solely on issuing a penalty without first attempting to understand the cause or provide guidance fails to uphold the collaborative and corrective nature often intended within regulatory frameworks. While penalties are a tool, they are typically a last resort or used for egregious violations. Ethically, an inspector should strive for compliance and education first. Another incorrect approach that involves overlooking the issue due to perceived minor impact disregards the CWA's zero discharge goal for pollutants and the cumulative effect of multiple minor discharges. This can lead to a degradation of water quality over time and undermines the integrity of the regulatory program. An approach that relies on anecdotal evidence or assumptions rather than documented observations and regulatory requirements is also professionally unsound. It introduces subjectivity and can lead to inconsistent enforcement, eroding trust in the inspection process. The professional decision-making process for similar situations should involve 1. Thoroughly observing and documenting site conditions, noting specific deviations from the Stormwater Pollution Prevention Plan, SWPP, or permit requirements. 2. Consulting the relevant CWA regulations, NPDES permit conditions, and the site's SWPP to confirm noncompliance. 3. Communicating findings clearly and professionally with the site operator, explaining the specific violations and referencing applicable regulations. 4. Discussing potential corrective actions and providing guidance on how to achieve compliance. 5. Establishing a reasonable timeframe for corrective actions and scheduling a follow-up inspection. 6. Escalating enforcement actions as necessary, based on the severity and persistence of the noncompliance and in accordance with established agency procedures. Question 2. System analysis indicates that a certified erosion, sediment, and stormwater inspector is evaluating a construction site. The inspector observes that the current land cover is primarily exposed soil with some areas of compacted gravel. The soil survey indicates a clay loam composition with moderate infiltration rates. Local weather forecasts predict a high-intensity rainfall event within the next 48 hours. Which of the following approaches best reflects the inspector's professional responsibility in assessing runoff generation potential? Option A. Emphasize the exposed soil and gravel land cover, recommending immediate stabilization without a detailed consideration of soil infiltration or rainfall intensity. Option B. Prioritize the clay loam soil type, assuming its moderate infiltration rate will mitigate the impact of the high-intensity rainfall regardless of land cover. Option C. Evaluate how the combination of clay loam soil, exposed soil and gravel land cover, and the predicted high-intensity rainfall will interact to influence infiltration, runoff volume, and velocity. Option D. Focus on the high-intensity rainfall forecast and recommend immediate implementation of extensive erosion control measures due to the potential for significant runoff. The correct answer is D. Focus on the high-intensity rainfall forecast and recommend immediate implementation of extensive erosion control measures due to the potential for significant runoff. Explanation: this scenario presents a common implementation challenge for a certified erosion, sediment, and stormwater inspector, accurately assessing the potential for runoff generation on a site with diverse characteristics. The challenge lies in integrating multiple influencing factors, rainfall intensity, soil type, and land cover into a practical, on-site evaluation that informs effective stormwater management. A professional inspector must move beyond simply observing the immediate conditions to predicting how those conditions will interact with anticipated weather events. The correct approach represents best professional practice because it demonstrates a comprehensive understanding of the hydrological principles governing runoff. It requires the inspector to not only identify the existing land cover and soil conditions, but also to consider the dynamic nature of rainfall. By evaluating how different rainfall intensities will interact with the specific soil infiltration rates and the permeability of the land cover, the inspector can accurately predict the volume and velocity of runoff. This predictive capability is crucial for selecting and verifying the efficacy of appropriate best management practices, BMP, as required by regulatory frameworks, ensuring compliance and environmental protection. This approach aligns with the ethical obligation to apply scientific knowledge and professional judgment to safeguard water resources. An incorrect approach that focuses solely on current land cover without considering soil type or rainfall intensity fails to account for the underlying hydrological potential of the site. This is a regulatory failure because it neglects key factors explicitly or implicitly addressed in stormwater management regulations, which aim to control runoff based on its generation potential. Ethically, it represents a dereliction of duty by providing an incomplete and potentially misleading assessment. Another incorrect approach that prioritizes only soil type while ignoring land cover and rainfall intensity is also flawed. While soil type is a significant factor in infiltration, it does not operate in isolation. A highly permeable soil can still generate substantial runoff if the land cover is impervious and the rainfall intensity is high. This approach is a regulatory failure as it overlooks the synergistic effects of multiple runoff influencing factors, leading to an inadequate assessment of risk. A third incorrect approach that solely considers rainfall intensity without evaluating the site's physical characteristics, soil and land cover, is equally problematic. Rainfall intensity is a critical input, but the site's ability to absorb or resist that rainfall is determined by its soil and cover. This approach is a regulatory and ethical failure because it bases the assessment on a single, external factor, ignoring the site-specific conditions that are the primary focus of an inspector's role in implementing and verifying stormwater controls. The professional decision-making process for similar situations involves a systematic multi-factor analysis. First, the inspector must understand the project's regulatory context and the specific requirements for stormwater management. Second, they must conduct a thorough site assessment, identifying and documenting all relevant factors: soil characteristics, texture, structure, permeability, existing and proposed land cover, vegetation type, density, impervious surfaces, and topography. Third, they must consider anticipated rainfall events, often guided by local precipitation data or project-specific design storm criteria. Finally, the inspector synthesizes this information to predict runoff generation and evaluate the adequacy of proposed or existing BMPs, ensuring compliance with all applicable regulations and best management practices. Question 3. During the evaluation of a construction site adjacent to a small perennial stream, an inspector observes widespread, shallow detachment of soil particles across a large, recently graded area, with minimal evidence of concentrated flow channels. Further downstream, along the stream's edge, the inspector notes undercut banks and sloughing of soil into the water. Which of the following best describes the primary erosion types present and the most appropriate initial focus for control measures? Option A. Rill erosion on the graded area and gully erosion along the stream bank, necessitating the installation of check dams and stream bank armoring. Option B. Sheet erosion on the graded area and stream bank erosion along the watercourse, requiring immediate stabilization of both. Option C. Sheet erosion on the graded area and rill erosion along the stream bank, indicating a need for surface roughening and vegetation establishment. Option D. Gully erosion on the graded area and stream bank erosion, requiring immediate diversion of concentrated flows and extensive grading. The correct answer is B. Sheet erosion on the graded area and stream bank erosion along the watercourse, requiring immediate stabilization of both. Explanation. This scenario is professionally challenging because it requires the certified erosion, sediment, and stormwater inspector to differentiate between various erosion types, each with distinct visual characteristics and implications for stormwater management and regulatory compliance. Misidentification can lead to incorrect control measure selection, inadequate mitigation, and potential noncompliance with federal, state, and local regulations, such as those mandated by the Clean Water Act and associated EPA guidelines. The inspector must apply their knowledge of erosion processes to a real-world site condition, considering the scale and severity of the observed erosion. The correct approach represents best professional practice because it accurately identifies the dominant erosion type based on observable evidence, and then proposes control measures directly addressing that specific type. This aligns with the fundamental principles of effective stormwater management and regulatory requirements, which emphasize targeted solutions for identified problems. For example, recognizing gully erosion necessitates different, more robust interventions than addressing minor sheet erosion. This precise identification ensures that resources are used efficiently and that the site's impact on receiving waters is minimized, fulfilling the inspector's duty to protect water quality. An incorrect approach that focuses solely on the most visually dramatic erosion without considering its underlying cause or other contributing erosion types would be professionally unacceptable. This could lead to a misdiagnosis and the implementation of ineffective or insufficient best management practices, BMP. For instance, applying only surface stabilization techniques to a site experiencing significant gully erosion might fail to address the deeper channel formation, leading to continued sediment transport and potential structural damage. This represents a failure to meet the professional standard of care and a potential violation of regulatory mandates to control sediment pollution. Another incorrect approach might be to overlook subtle but significant erosion types, such as stream bank erosion, in favor of more obvious surface erosion. This is problematic because stream bank erosion can be a major source of sediment and can destabilize adjacent areas, impacting water quality and infrastructure. Failing to identify and address it demonstrates a lack of thoroughness and a potential oversight of critical environmental risks, which is contrary to the inspector's responsibility to conduct a comprehensive evaluation. A professional decision-making process for similar situations involves a systematic site assessment. This includes observing the overall landscape, identifying areas of disturbed soil, and then closely examining the characteristics of any observed soil movement. The inspector should look for evidence of water flow patterns, the depth and width of channels, the extent of soil detachment, and the transport of sediment. Comparing these observations against established definitions and visual guides for sheet, rill, gully, and stream bank erosion is crucial. Once the dominant and contributing erosion types are identified, the inspector can then select appropriate BMPs that are specifically designed to mitigate those particular forms of erosion, ensuring compliance and effective environmental protection. Question 4. The performance metrics show a significant amount of fine-grained sediment being discharged from the site's stormwater outfall, despite the presence of a sediment basin and silt fences. As a certified erosion, sediment, and stormwater inspector, What is the most appropriate initial step to assess the effectiveness of the current erosion and sediment control measures? Option A. Conclude that the sediment basin and silt fences are inadequate and immediately recommend the installation of additional, larger sediment traps. Option B. Observe the water column and streambed at the outfall and upstream to determine if sediment is primarily being transported in suspension, saltation, or traction, and evaluate if the installed BMPs are designed to address these specific transport mechanisms. Option C. Focus solely on the volume of sediment observed at the outfall and recommend increasing the frequency of BMP maintenance without analyzing the transport processes. Option D. Assume the sediment is a result of an unusually intense rainfall event and document the observation without further investigation into BMP performance. The correct answer is B. Observe the water column and streambed at the outfall and upstream to determine if sediment is primarily being transported in suspension, saltation, or traction, and evaluate if the installed BMPs are designed to address these specific transport mechanisms. Explanation. Scenario analysis. This scenario presents a common implementation challenge for a certified erosion, sediment, and stormwater inspector, SESI, where observed site conditions do not align with expected performance based on installed best management practices, BMP. The challenge lies in accurately diagnosing the cause of sediment transport despite the presence of BMPs, which requires a nuanced understanding of sediment transport processes and their interaction with stormwater management. The inspector must move beyond simply identifying the presence of sediment to understanding how it is moving, and why the BMPs are not fully effective. This requires careful observation and application of knowledge regarding suspension, saltation, and traction. Correct approach analysis. The correct approach involves a systematic evaluation of the site's sediment transport dynamics in relation to the installed BMPs. This means observing the physical characteristics of the sediment and the flow regime to determine the dominant transport mechanisms. If fine particles are observed suspended in the water column and being carried downstream, it indicates suspension. If larger particles are seen bouncing along the streambed, it points to saltation. If the largest particles are rolling or sliding, it signifies traction. Understanding these processes allows the inspector to assess if the BMPs are designed and functioning to capture sediment based on its size and mode of transport. For instance, a sediment basin might be effective for traction and saltation, but less so for fine suspended particles, requiring additional treatment like filtration or chemical stabilization. This approach aligns with the SESI responsibility to ensure BMPs are effectively preventing sediment pollution, as mandated by regulatory frameworks, such as the U.S. EPA's Stormwater Management Program, guidance, and state-specific stormwater regulations that require effective erosion and sediment control. Incorrect approaches analysis. One incorrect approach would be to solely focus on the presence of sediment without analyzing its transport mechanism. This might lead to a superficial conclusion that the BMPs are failing without understanding the root cause. For example, if fine suspended sediment is the primary issue, and the inspector only notes the presence of sediment in a basin designed for larger particles, they might incorrectly recommend adjustments to the basin's outlet without addressing the fundamental problem of fine particle capture. This fails to meet the regulatory requirement of effectively controlling sediment pollution. Another incorrect approach would be to assume that because BMPs are installed, they must be functioning correctly, and any observed sediment is due to an extreme weather event or external factors not related to the construction activity. This overlooks the inspector's duty to verify the effectiveness of BMPs and identify deficiencies. Regulatory frameworks require ongoing monitoring and assessment of BMP performance, and attributing sediment transport solely to external factors without thorough investigation is a dereliction of duty. A third incorrect approach would be to recommend a BMP that is not appropriate for the observed sediment transport process. For instance, if the primary issue is suspended fine sediment, recommending only a silt fence, which is primarily effective for trapping sediment in traction and some saltation, would be an ineffective and potentially non-compliant solution. This demonstrates a lack of understanding of how different BMPs interact with various sediment transport mechanisms, leading to non-compliance with stormwater management objectives. Professional reasoning. When faced with observed sediment transport, assessee should employ a decision-making process that begins with detailed site observation. This involves identifying the type of sediment, its location, and the flow conditions. The inspector should then apply their knowledge of sediment transport processes, suspension, saltation, traction, to characterize the dominant mechanisms at play. Based on this characterization, they should evaluate the suitability and performance of the installed BMPs against these mechanisms. If the BMPs are not effectively controlling the observed sediment transport, the inspector must identify the specific deficiencies and recommend corrective actions that are scientifically sound and regulatory compliant. This process ensures that interventions are targeted, effective, and uphold the professional and ethical obligations of assessee to protect water quality. Question 5. The audit findings indicate that a construction site has implemented several erosion and sediment control measures, including silt fences and sediment basins. However, during a site inspection, the inspector observes significant bank erosion along a stream adjacent to the site, with noticeable material entering the watercourse. While the sediment basins appear to be capturing some suspended sediment, the stream itself shows signs of increased turbidity and deposition of coarser material along its bed. Considering the regulatory framework for certified erosion, sediment, and stormwater inspectors, which approach best reflects the inspector's responsibility in assessing the site's compliance regarding sediment load? Option A. Prioritize the visual appearance of the sediment basins and silt fences, assuming that if they are present and appear functional, the site is in compliance regardless of downstream impacts. Option B. Focus solely on the effectiveness of the silt fences and sediment basins in capturing suspended sediment, as these are the primary visible controls. Option C. Evaluate the overall impact of site activities on the stream sediment regime, considering both suspended sediment and bed load contributions, and the adequacy of controls to manage the total sediment load. Option D. Document the visible sediment plumes in the stream and recommend immediate removal of the deposited material, without further investigation into the source or type of sediment. Correct answer is B. Focus solely on the effectiveness of the silt fences and sediment basins in capturing suspended sediment, as these are the primary visible controls. Explanation. This scenario is professionally challenging because it requires an inspector to differentiate between various forms of sediment transport and their implications for stormwater management, even when visual cues might be ambiguous. The inspector must apply a nuanced understanding of sediment dynamics to accurately assess compliance with regulatory requirements, which often focus on controlling the total sediment load impacting receiving waters, not just one component. The correct approach represents best professional practice because it acknowledges that effective stormwater management and erosion control aim to minimize the overall discharge of sediment into waterways. This includes understanding that while suspended sediment is often the most visible and directly regulated component, bed load and total sediment load are critical indicators of the overall sediment transport process. By considering the total sediment load, the inspector is evaluating the comprehensive impact of site activities on water quality and aquatic habitats, aligning with the overarching goals of regulations like the U.S. EPA's National Pollutant Discharge Elimination System, NPDES, stormwater program. This holistic view ensures that all potential sources and pathways of sediment are considered, leading to more robust and effective control measures. An incorrect approach that focuses solely on suspended sediment load fails to address the full scope of sediment transport. While suspended sediment is a primary concern for turbidity and aquatic life, ignoring bed load can lead to an underestimation of the total sediment contribution. Bed load, though less visible, can significantly impact stream morphology, habitat quality, and downstream sediment accumulation. Ethically and regulatorily, this narrow focus could result in non-compliance if the site's activities are causing substantial bed load movement that, in aggregate with suspended sediment, exceeds acceptable thresholds or contributes to channel degradation. Another incorrect approach that prioritizes only visible sediment plumes overlooks the less apparent but equally damaging forms of sediment transport. Sediment plumes are a symptom, and focusing only on them without understanding the underlying causes, which could include significant bed load movement or high rates of suspended sediment generation that haven't yet formed a visible plume, is reactive rather than proactive. This approach fails to identify and address the root causes of sediment pollution, potentially leading to ongoing noncompliance and environmental harm. It also neglects the regulatory requirement to implement controls that prevent sediment from reaching waters in the first place, not just to manage visible discharges. A professional decision-making process for similar situations should involve a systematic evaluation of the site's activities in relation to the entire sediment transport cycle. This begins with understanding the site's topography, soil types, and the nature of ongoing land-disturbing activities. The inspector should then assess the effectiveness of installed erosion and sediment control measures, ESCOM, in managing all forms of sediment. This involves observing for signs of active erosion, the presence of sediment in drainage channels, and evidence of sediment deposition. Crucially, the inspector must consider the potential for both suspended sediment and bed load movement, even if only one is immediately apparent. If there is evidence of significant erosion or sediment accumulation, the inspector should investigate the underlying causes and evaluate whether the ESCOM are adequately addressing the total sediment load being generated and transported. This requires a thorough understanding of the regulatory framework's intent to protect water quality and aquatic ecosystems from the detrimental effects of excessive sediment. Question 6. Regulatory review indicates that a construction site's soil texture is crucial for determining the appropriate erosion and sediment control measures, as per the Certified Erosion, Sediment, and Stormwater Inspector Guidelines. During a site inspection, you visually assess the soil and determine it to be a sandy loam. However, the project specifications require a more precise understanding of the sand, silt, and clay percentages to ensure compliance with specific stormwater infiltration rates. The contractor states that sandy loam is sufficient and that further testing is unnecessary. What is the most appropriate course of action? Option A. Inform the contractor that while visual assessment is a starting point, the project specifications necessitate a more precise determination of soil texture and recommend further testing if they cannot provide it. Option B. Proceed with the inspection based on the visual sandy loam classification, assuming that minor variations in soil composition will not significantly impact the effectiveness of the chosen erosion and sediment control measures. Option C. Accept the contractor's assertion that sandy loam is sufficient, as visual assessment is generally adequate for most site inspections. Option D. Recommend or perform a more objective method to determine the precise percentages of sand, silt, and clay, as required by the project specifications, to ensure accurate compliance with infiltration rate requirements. The correct answer is D. Recommend or perform a more objective method to determine the precise percentages of sand, silt, and clay, as required by the project specifications, to ensure accurate compliance with infiltration rate requirements. Explanation. Scenario analysis. This scenario presents a professional challenge because the inspector is tasked with evaluating a site's soil texture, a fundamental factor in erosion and sediment control, but is faced with conflicting information and a potential pressure to overlook a critical detail. The challenge lies in balancing the need for accurate site assessment with external influences, ensuring that professional judgment is not compromised by expediency or misinterpretation. The inspector must rely on their understanding of soil science and regulatory requirements to make an informed decision. Correct approach analysis. The correct approach involves recognizing that the visual assessment of soil texture, while a useful initial step, is insufficient for definitive classification when specific regulatory requirements mandate a more precise understanding. Best professional practice dictates that when visual cues suggest a particular soil texture, e.g., sandy loam, but the regulatory framework or project specifications require confirmation of specific percentages of sand, silt, and clay for design or compliance purposes, the inspector must advocate for or perform a more objective method. This aligns with the ethical obligation to uphold the integrity of the inspection process and ensure that site management practices are based on accurate data, as required by the Certified Erosion, Sediment, and Stormwater Inspector Program's commitment to environmental protection and regulatory adherence. The inspector's role is to verify compliance with established standards, and if those standards necessitate a quantitative understanding of soil texture, then visual estimation alone is inadequate. Incorrect approach is analysis. One incorrect approach is to rely solely on the visual assessment of sandy loam and assume it meets all project requirements without further verification. This fails to acknowledge that regulatory frameworks often have specific performance standards or design parameters tied to precise soil texture classifications. Ethically, this represents a dereliction of duty by not ensuring the accuracy of critical site data. It also risks noncompliance with project specifications or underlying environmental regulations that may depend on a more granular understanding of soil composition. Another incorrect approach is to defer entirely to the contractor's assertion about the soil texture without independent verification, especially if the visual assessment suggests otherwise or if the project specifications are unclear. This compromises the inspector's professional independence and objectivity. It is an ethical failure to abdicate responsibility for site assessment and a regulatory failure to not independently verify compliance with established standards. A third incorrect approach is to dismiss the need for precise soil texture determination because the visual assessment appears close enough to a general classification. This demonstrates a lack of understanding of how subtle variations in sand, silt, and clay content can significantly impact soil properties like permeability, erodibility, and compaction potential, which are directly relevant to stormwater management and erosion control. This approach is both a regulatory failure, as it may not meet the specific requirements of the applicable framework, and an ethical failure, as it prioritizes convenience over thoroughness and accuracy. Professional reasoning. Professionals in this role should adopt a decision-making process that prioritizes accuracy, objectivity, and adherence to regulatory mandates. When faced with potential discrepancies or ambiguities, the process should involve 1. Thoroughly understanding the specific requirements of the applicable regulatory framework and project specifications regarding soil texture. 2. Conducting an initial visual assessment as a preliminary step. 3. If the visual assessment is insufficient for definitive classification, or if there is any doubt, seeking clarification or recommending further, more objective testing, e.g., field method hydrometer analysis to confirm soil composition. 4. Documenting all observations, assessments, and recommendations meticulously. 5. Communicating findings and any necessary actions clearly and professionally to all relevant parties. This systematic approach ensures that professional judgment is informed by data and that the integrity of the inspection process is maintained. Question 7. Compliance review shows that during a routine site inspection, a certified erosion, sediment, and stormwater inspector observed significant sediment tracking from a construction site onto a public roadway, clearly violating the site's stormwater pollution prevention plan, SWPPPP, and local ordinances. The site superintendent, aware of the issue, asks the inspector to look the other way this time, promising to address it immediately after the current concrete pour is completed later that day, and suggesting that a formal report might complicate their schedule. What is the most appropriate professional course of action for the inspector? Option A. Document the observed sediment tracking, clearly referencing the specific SWPPP requirements and local ordinances being violated, and issue a formal notice of noncompliance with a clear directive for immediate corrective action and a specified follow-up inspection timeline. Option B. Document the sediment tracking and verbally inform the site superintendent of the violation, but refrain from issuing a formal report to avoid creating unnecessary administrative burden for the site and the inspector. Option C. Inform the site superintendent that the sediment tracking is a minor issue that does not warrant a formal report at this time, given the contractor's commitment to address it, and proceed with the rest of the inspection. Option D. Advise the site superintendent that while the issue is noted, the inspector will defer formal reporting until after the concrete pour is complete, trusting their assurance of immediate correction, and will revisit the site in a few days. Correct answer is A. Document the observed sediment tracking, clearly referencing the specific SWPPP requirements and local ordinances being violated, and issue a formal notice of noncompliance with a clear directive for immediate corrective action and a specified follow-up inspection timeline. Explanation. This scenario presents a common ethical dilemma for a certified erosion, sediment, and stormwater inspector, SESWI, where professional judgment is tested against potential external pressures. The challenge lies in balancing the imperative to uphold regulatory compliance and environmental protection with the desire to maintain a positive working relationship with a client or contractor. The inspector must recognize that their primary responsibility is to the integrity of the inspection process and the enforcement of regulations, not to the convenience or financial interests of the site owner or contractor. The correct approach represents best professional practice because it prioritizes adherence to the established regulatory framework and the SESWI Code of Ethics. By documenting the observed deficiencies accurately and recommending corrective actions in accordance with the relevant regulations, e.g., EPA's Stormwater Program, state-specific stormwater management manuals, or local ordinances, the inspector upholds their professional integrity and ensures the site is managed in a way that minimizes environmental impact. This approach is grounded in the SESWI duty to protect water quality and prevent pollution, as mandated by federal and state environmental laws. An incorrect approach that involves overlooking or downplaying identified noncompliance issues, even with the promise of future correction, represents a significant regulatory and ethical failure. This undermines the purpose of the inspection program, which is to ensure immediate compliance and prevent ongoing environmental harm. It can lead to continued sediment runoff, pollution of waterways, and potential legal liabilities for the inspector, the client, and the regulatory agency. Furthermore, such an approach erodes public trust in the inspection process and the environmental protection efforts it supports. Another incorrect approach, such as accepting a verbal assurance of future compliance without proper documentation or a clear corrective action plan, fails to establish a verifiable record of the site's condition and the agreed-upon remediation. This leaves the situation ambiguous and makes it difficult to hold parties accountable if the promised corrections are not made. It also bypasses the established procedures for addressing noncompliance, which typically involve written documentation and timelines for corrective actions. The professional reasoning process for similar situations should involve a clear understanding of the SESWI responsibilities as outlined in their certification guidelines and applicable regulations. Inspectors must first identify and accurately document any deviations from the approved Stormwater Pollution Prevention Plan, SWPPP, or regulatory requirements. They should then consult the relevant regulations and their professional code of ethics to determine the appropriate course of action. If noncompliance is identified, the inspector must clearly communicate the deficiencies to the responsible party, referencing specific regulatory requirements, and recommend concrete corrective actions with a defined timeline. Maintaining objective documentation throughout the process is paramount. When faced with pressure to overlook issues, the inspector must firmly but professionally reiterate their obligations and the potential consequences of non-compliance. Question 8. The performance metrics show a significant amount of fine sediment being transported off a construction site. During the last inspection period, there were several days of moderate rainfall and consistent, strong winds. The site has exposed soil stockpiles and areas of recently graded earth on moderate slopes. Which primary soil erosion mechanism is most likely responsible for the observed sediment transport, given these conditions? Option A. Primarily concentrated runoff in defined channels, leading to significant scour and sediment entrainment. Option B. Predominantly gravity-driven mass wasting due to the saturation of steep slopes. Option C. Solely wind erosion, evidenced by widespread dust generation across the site. Option D. A combination of rainfall-induced sheet and rill erosion, exacerbated by wind-driven detachment and transport of dry surface particles. The correct answer is D. A combination of rainfall-induced sheet and rill erosion, exacerbated by wind-driven detachment and transport of dry surface particles. Explanation. Scenario analysis. This scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors, interpreting site conditions and identifying the primary drivers of erosion to ensure compliance with regulatory requirements. The challenge lies in distinguishing between the effects of different erosion mechanisms, as multiple factors can be at play simultaneously. Accurate identification is crucial for selecting appropriate best management practices, BMP, and preventing noncompliance, which can lead to fines, project delays, and environmental damage. The inspector must apply their knowledge of soil mechanics, hydrology, and meteorology within the specific regulatory framework to make a sound judgment. Correct approach analysis. The correct approach involves a systematic assessment of the site, considering the prevailing weather conditions and observable evidence of soil movement. For rainfall-induced erosion, an inspector would look for evidence of rills, gullies, and sheet erosion, particularly on exposed soil surfaces and slopes, and correlate this with recent or ongoing precipitation events. For runoff, the focus would be on identifying concentrated flow paths, scour at culverts or drainage structures, and sediment deposition downstream. Wind erosion evidence includes dust plumes, sandblasting of surfaces, and deposition of fine material in sheltered areas, especially during dry, windy periods. Gravity erosion is typically observed on steep slopes as mass movement, such as shallow slides or creep, often exacerbated by saturation. The correct approach prioritizes the most evident and impactful mechanism based on the observed conditions and recent environmental factors, aligning with the goal of the regulatory framework to control sediment pollution from construction sites. Incorrect approach is analysis. Focusing solely on one mechanism without considering others is a regulatory failure. For instance, attributing all observed soil movement to rainfall when significant wind activity has also occurred ignores a contributing factor, potentially leading to the selection of ineffective BMPs. Similarly, overlooking the role of gravity on a steep slope because runoff is also present means a critical erosion pathway is unaddressed. A failure to consider the interplay of these forces, or to prioritize the dominant mechanism based on evidence, constitutes a lapse in professional judgment and a failure to meet the inspector's duty to ensure comprehensive erosion control as mandated by regulations. This can result in continued sediment discharge, violating permit conditions. Professional reasoning. A certified erosion, sediment, and stormwater inspector must adopt a holistic and evidence-based approach. The decision-making process should involve 1. Observing and documenting site conditions, including soil type, slope, vegetative cover, and exposed areas. 2. Correlating observations with recent weather data, rainfall intensity and duration, wind speed and direction. 3. Identifying visible signs of erosion and sediment transport. 4. Determining the dominant erosion mechanism, based on the totality of evidence. And 5. Selecting and verifying BMPs that effectively address the identified mechanisms in accordance with the applicable regulatory framework. This systematic process ensures that all significant erosion risks are identified and managed, fulfilling the inspector's responsibility to protect water quality. Question 9. Implementation of a phased corrective action plan for a construction site experiencing significant sediment runoff, focusing on optimizing the effectiveness of erosion and sediment control measures while ensuring regulatory compliance. Option A. Immediately install additional sediment traps and barriers downstream of the current problem areas without investigating the upstream causes of the excessive erosion. Option B. Conduct a detailed site assessment to identify the primary sources of erosion and the specific reasons for the failure of existing controls. Then develop a plan that addresses these root causes with appropriate site-specific BMPs, prioritizing immediate stabilization and long-term effectiveness. Option C. Propose a temporary, low-cost solution to mitigate the immediate visible sediment runoff, deferring a more comprehensive assessment and permanent fixes to a later stage. Option D. Document the observed sediment runoff and issue a notice of violation without providing any recommendations for corrective actions. The correct answer is B. Conduct a detailed site assessment to identify the primary sources of erosion and the specific reasons for the failure of existing controls. Then develop a plan that addresses these root causes with appropriate site-specific BMPs, prioritizing immediate stabilization and long-term effectiveness. Explanation. This scenario is professionally challenging because it requires the inspector to balance the immediate need for site stabilization with the long-term effectiveness and regulatory compliance of erosion and sediment control measures. The inspector must not only identify deficiencies, but also recommend or approve corrective actions that are practical, cost-effective, and adhere to the established regulatory framework. The challenge lies in ensuring that the chosen solutions are not merely superficial fixes, but address the root causes of erosion and sediment transport, thereby preventing future non-compliance and environmental damage. The correct approach represents best professional practice because it prioritizes a comprehensive assessment of the site's hydrological conditions and the effectiveness of existing controls. By recommending a phased approach that addresses both immediate risks and underlying issues, the inspector ensures that the corrective actions are sustainable and compliant with the spirit and letter of the regulations. This proactive and thorough method minimizes the likelihood of recurring problems, reduces the potential for off-site impacts, and demonstrates a commitment to environmental stewardship, which is a core ethical and regulatory expectation for certified inspectors. An incorrect approach that focuses solely on adding more structural controls without evaluating their placement or the underlying causes of failure is professionally unacceptable. This represents a regulatory failure because it may not adequately address the source of the sediment pollution and could lead to continued non-compliance. Ethically, it fails to provide the most effective solution for environmental protection. Another incorrect approach that involves simply documenting the problem without proposing actionable solutions is also a regulatory and ethical failure. Inspectors have a professional responsibility to guide the responsible party towards compliance, not just to identify violations. Finally, an approach that suggests a quick, temporary fix without considering long-term stability or regulatory requirements demonstrates a lack of due diligence and can lead to repeated issues, undermining the credibility of the inspector and the effectiveness of the control program. Professionals should use a decision-making framework that begins with a thorough understanding of the site's specific conditions and the applicable regulations. This involves observing the site's topography, soil types, drainage patterns, and the performance of existing best management practices, BMP. The next step is to identify the specific causes of erosion and sediment transport. Based on this analysis, the inspector should then evaluate potential corrective actions, considering their effectiveness, feasibility, cost, and compliance with regulatory standards. The decision should always favor solutions that provide the most robust and sustainable protection against erosion and sediment pollution, aligning with both regulatory mandates and professional ethics. Question 10. Operational review demonstrates significant fine sediment deposition in the downstream receiving stream adjacent to a construction site. The site has several active erosion control measures in place, including silt fences and a sediment basin. The inspector observes that the silt fences appear to be functioning as intended, with some sediment accumulation behind them, and the sediment basin has a substantial volume of settled material. However, the fine sediment in the stream is primarily silt and clay. Considering the principles of sediment transport, which of the following is the most likely primary factor contributing to the observed fine sediment deposition in the receiving stream, given the site conditions? Option A. The soil type on the construction site is inherently prone to generating large, heavy sediment particles that overwhelm BMPs. Option B. Upstream erosion from areas not covered by active stabilization measures is introducing a high volume of coarse sediment that is then being transported downstream. Option C. The flow velocity in the receiving stream is sufficiently low to allow fine particles, which are easily transported, to settle out. Option D. The sediment basin is not designed to capture particles of silt and clay size, and runoff is bypassing the basin's settling capacity. The correct answer is C. The flow velocity in the receiving stream is sufficiently low to allow fine particles, which are easily transported, to settle out. Explanation. Scenario analysis. This scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors, identifying the root cause of sediment deposition in a receiving water body when multiple contributing factors are present. The challenge lies in accurately assessing the interplay between flow velocity, particle size, and the effectiveness of existing best management practices, BMP, to determine the most significant driver of the observed deposition. A failure to correctly diagnose the cause can lead to ineffective remediation efforts, continued environmental damage, and potential regulatory noncompliance. Correct approach analysis. The correct approach involves a systematic evaluation of the site conditions and BMP performance, directly linking observed sediment deposition to the physical principles of sediment transport. This means recognizing that higher flow velocities can transport larger and heavier particles, while lower velocities lead to the deposition of finer sediments. The inspector must assess if the existing BMPs are adequately reducing flow velocity and capturing sediment particles of the sizes being transported from the site. For instance, if fine silts and clays are observed in the deposition, it suggests that either the flow velocity is not being sufficiently reduced by BMPs, or the BMPs are not designed to capture such fine particles effectively. Conversely, if larger sand particles are found, it points to higher velocities or inadequate sediment trapping. This approach aligns with the fundamental principles of erosion and sediment control, emphasizing a data-driven assessment of BMP effectiveness against the physical processes at play, as mandated by regulatory frameworks that require effective control of sediment runoff. Incorrect approaches analysis. Focusing solely on the presence of fine sediment without considering flow velocity is a regulatory failure because it ignores a primary factor influencing deposition. Fine particles can remain suspended in higher velocities and only settle out when flow slows down significantly. Attributing deposition solely to fine particle size without assessing velocity means the inspector might overlook inadequate flow dissipation or sediment settling time within BMPs. Assuming all sediment is a result of BMP failure without investigating upstream erosion sources is an ethical and regulatory failure. While BMPs are critical, they are designed to manage sediment generated from disturbed areas. If significant erosion is occurring upstream of the BMPs due to inadequate stabilization, the BMPs may be overwhelmed, leading to deposition. A thorough inspection requires identifying the origin of the sediment. Concluding that sediment deposition is unavoidable due to the nature of the soil, regardless of site conditions or BMP performance, represents a failure to uphold professional responsibility and regulatory requirements. Regulations mandate that reasonable and practicable measures be taken to minimize sediment pollution. Dismissing the issue based on soil type without evaluating site management and BMP effectiveness is a dereliction of duty and a violation of the principle of diligent effort in environmental protection. Professional reasoning. Professionals should approach such scenarios by first understanding the site's disturbed areas and the pathways of stormwater runoff. They must then evaluate the performance of each BMP in relation to the type and volume of sediment being generated and transported. This involves observing flow velocities within and exiting BMPs, assessing the particle size distribution of the sediment in the runoff and in the receiving water body, and examining the condition and maintenance of the BMPs. The decision-making process should follow a hierarchy. Identify erosion sources, assess transport mechanisms, influenced by velocity, evaluate BMP effectiveness in capturing sediment of specific particle sizes, and finally, determine if remediation or maintenance is required to meet regulatory standards. This systematic, principle-based approach ensures that the most effective and compliant solutions are identified. Question 11. The audit findings indicate that a recent stormwater inspection report for a construction site relied heavily on the numerical output of the revised Universal Soil Loss Equation, Russell, to identify areas of concern. The inspector's report primarily focused on the calculated soil loss values without conducting detailed on-site verification of the specific factors contributing to those values or observing the actual presence of erosion. Which of the following approaches best reflects a professionally sound and regulatory compliant method for utilizing Russell in erosion prediction for a stormwater inspection? Option A. Disregard Russell calculations entirely, as they are theoretical and do not represent actual observed erosion on a construction site. Option B. Focus solely on the rainfall erosivity R factor and soil erodibility K factor, components of Russell, as these are the most objective and easily quantifiable elements. Option C. Accept the numerical outputs of Russell as definitive predictions of erosion and base all BMP recommendations solely on these calculated values. Option D. Use Russell outputs as a preliminary risk assessment tool to guide detailed site-specific investigations and the selection of appropriate best management practices, BMP. The correct answer is D. Use Russell outputs as a preliminary risk assessment tool to guide detailed site-specific investigations and the selection of appropriate best management practices, BMP. Explanation. This scenario presents a professional challenge because it requires the certified erosion, sediment, and stormwater inspector to interpret and apply complex predictive models, Russell, in a real-world context, moving beyond simple observation to proactive risk assessment. The challenge lies in understanding the limitations of these models and how to use their outputs to inform practical, site-specific management decisions, rather than treating them as absolute predictors. Careful judgment is required to balance the theoretical outputs of the equations with the practical realities of site conditions and available resources. The correct approach represents best professional practice because it acknowledges that Russell are tools for estimating potential erosion, not definitive predictions of actual erosion. Best practice involves using the model outputs as a basis for identifying areas of higher risk, and then conducting site-specific evaluations to confirm these risks and develop targeted best management practices, BMP. This aligns with regulatory frameworks that emphasize a proactive, risk-based approach to stormwater management and erosion control, requiring inspectors to not only identify existing problems, but also to anticipate potential issues and recommend preventative measures. This approach demonstrates a thorough understanding of the underlying principles of erosion and sediment transport and the practical application of predictive tools. An incorrect approach that relies solely on the numerical output of the USL/Russell without site verification fails to meet professional standards. This is a regulatory failure because it bypasses the requirement for site-specific assessment and the selection of appropriate BMPs tailored to actual conditions. Ethically, it represents a dereliction of duty by not ensuring that the most effective and efficient control measures are implemented. Another incorrect approach that dismisses the USL/Russell entirely as irrelevant to site inspection is also professionally unacceptable. This is a regulatory failure because it ignores established methodologies for erosion prediction that are often referenced or required by stormwater management plans and permits. It demonstrates a lack of understanding of the tools available for proactive risk assessment, which is a core competency for an inspector. Ethically, it suggests an unwillingness to engage with the full scope of responsibilities, potentially leading to missed opportunities for effective erosion control. A third incorrect approach that focuses only on the most easily quantifiable factors within the USL/Russell, ignoring qualitative site observations, is also flawed. This is a regulatory failure because it leads to an incomplete and potentially inaccurate assessment of erosion risk. The models are designed to be used holistically, and ignoring key qualitative factors like ground cover condition or the presence of rills and gullies can lead to misidentification of high-risk areas. Ethically, it represents a superficial application of the tools, failing to provide the comprehensive evaluation expected of a professional inspector. The professional decision-making process for similar situations should involve 1. Understanding the purpose and limitations of predictive tools like USL/Russell. 2. Using model outputs as a guide for prioritizing site investigations. 3. Conducting thorough site-specific assessments to validate or refine the model's predictions. 4. Developing BMP recommendations that are directly informed by both the predictive models and the site-specific observations. 5. Documenting the entire process, including how model outputs were used and how site conditions influenced final recommendations. Question 12. Compliance review shows a construction site operator is concerned about potential project delays due to ongoing sediment runoff into a nearby stream. The operator claims the sediment is minor and poses no significant threat to water quality or aquatic life, urging the inspector to overlook the issue to avoid halting operations. As a certified erosion, sediment, and stormwater inspector, what is the most appropriate course of action? Option A. Accept the operator's assessment that the sediment is minor and poses no significant threat, and advise them to continue operations while monitoring the situation informally. Option B. Focus solely on the immediate cost of implementing additional sediment controls, advising the operator to choose the least expensive option without a full assessment of its effectiveness or regulatory compliance. Option C. Immediately issue a stop work order for all site activities until the operator can definitively prove that no sediment is reaching the stream, regardless of visual evidence. Option D. Conduct a thorough, site-specific assessment of the sedimentation impacts, documenting observed conditions and comparing them against relevant regulatory standards and permit requirements to determine compliance and necessary corrective actions. The correct answer is D. Conduct a thorough, site-specific assessment of the sedimentation impacts, documenting observed conditions, and comparing them against relevant regulatory standards and permit requirements to determine compliance and necessary corrective actions. Explanation. Scenario analysis. This scenario is professionally challenging because it requires the inspector to balance the immediate needs of a stakeholder with the long-term environmental protection mandated by regulations. The stakeholder's desire to minimize project delays, driven by economic concerns, can create pressure to overlook or downplay sedimentation impacts. The inspector must navigate this pressure while adhering strictly to the Certified Erosion, Sediment and Stormwater Inspector (SESI) standards and relevant U.S. federal and state regulations, e.g., Clean Water Act, EPA guidance, state-specific stormwater management programs. The challenge lies in objectively assessing the severity of sedimentation impacts and communicating them effectively to the stakeholder, ensuring compliance without undue obstruction of legitimate development. Correct approach analysis. The correct approach involves a thorough, site-specific assessment of sedimentation impacts, referencing established monitoring protocols and regulatory thresholds. This approach prioritizes data-driven conclusions and adherence to the SESI Code of Ethics, which mandates professional integrity and environmental stewardship. By documenting observed impacts, e.g., turbidity levels, silt deposition in receiving waters, visible habitat degradation, and comparing them against permit requirements or established water quality standards, the inspector provides an objective basis for their findings. This ensures that any required corrective actions are justified and directly address the identified noncompliance, thereby protecting water quality, aquatic habitats, and downstream infrastructure as intended by the regulatory framework. Incorrect approaches analysis. One incorrect approach involves accepting the stakeholder's assertion that the sedimentation is minor without independent verification. This fails to uphold the inspector's duty to independently assess compliance. Ethically, it represents a dereliction of duty and a potential violation of the SESI Code of Conduct, which requires diligent inspection. Legally, it could lead to continued noncompliance with the Clean Water Act and state stormwater regulations, potentially resulting in enforcement actions against the project and the inspector's certification. Another incorrect approach is to immediately halt all site activities based solely on the stakeholder's complaint, without a proper assessment. This demonstrates a lack of professional judgment and an overreaction that can cause unnecessary economic hardship and project delays, potentially exceeding regulatory requirements for immediate action. While prompt action is sometimes necessary, it must be based on a reasoned evaluation of the risks and regulatory mandates, not on an unsubstantiated claim or a desire to avoid conflict. This approach fails to follow the systematic, evidence-based process expected of a certified inspector. A third incorrect approach is to focus solely on the immediate cost of remediation without considering the long-term consequences of sedimentation. This is a narrow, economically driven perspective that ignores the core purpose of erosion and sediment control regulations, protecting environmental resources. It fails to acknowledge the regulatory mandate to prevent water quality degradation, habitat destruction, and infrastructure damage, which are often cumulative and can be more costly to address in the long run than proactive control measures. This approach also neglects the ethical obligation of the inspector to advocate for environmental protection. Professional reasoning. Professionals should adopt a systematic, evidence-based approach. This involves 1. Understanding the specific regulatory requirements and permit conditions applicable to the site. 2. Conducting a thorough on-site inspection to observe and document all relevant conditions, including the extent and nature of sedimentation and its potential impacts. 3. Utilizing appropriate monitoring tools and techniques to gather objective data, e.g., turbidity meters, visual assessments of stream beds. 4. Comparing findings against established benchmarks and regulatory thresholds. 5. Communicating findings clearly and professionally to the stakeholder, explaining the regulatory basis for any required actions. 6. Recommending specific, practical corrective actions that will bring the site into compliance. 7. Maintaining detailed records of all inspections, findings, and communications. This process ensures objectivity, regulatory compliance, and effective environmental protection. Question 13. Investigation of a proposed commercial development site reveals varied topography, including areas of dense woodland, open grassy fields, and a small intermittent stream. The project plans include extensive grading, excavation, and the construction of a large parking lot. As a certified erosion, sediment, and stormwater inspector, which approach is most effective for identifying potential erosion and sediment sources during the pre-construction planning phase, adhering strictly to U.S. EPA and relevant state stormwater regulations. Option A. Rely solely on visual inspection of existing vegetation density, assuming that areas with thicker plant cover will naturally prevent significant erosion during construction. Option B. Primarily focus on the areas with the most visible existing erosion, assuming that future construction will exacerbate these known problem spots. Option C. Conduct a thorough site walkthrough, analyzing topographic features, identifying soil types through observation and available soil surveys, and assessing how proposed grading and construction activities will alter natural drainage patterns and potentially destabilize soil. Option D. Concentrate efforts on identifying only the steepest slopes on the site, as these are inherently the most prone to erosion regardless of other site conditions or planned activities. Correct answer is C. Conduct a thorough site walkthrough, analyzing topographic features, identifying soil types through observation and available soil surveys, and assessing how proposed grading and construction activities will alter natural drainage patterns and potentially destabilize soil. Explanation. The scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors. Identifying potential erosion and sediment sources during the pre-construction phase on a site with varied topography and existing vegetation. The challenge lies in accurately predicting where and how stormwater runoff will behave and impact the soil before any ground disturbance occurs. This requires a thorough understanding of site hydrology, soil types, and the potential effects of planned construction activities. Careful judgment is essential to avoid overlooking critical areas that could lead to significant environmental damage and regulatory noncompliance. The correct approach involves a systematic site assessment that integrates topographic analysis, soil characterization, and an understanding of proposed land-disturbing activities. This method directly aligns with the principles of effective stormwater management and erosion control mandated by regulatory frameworks such as the U.S. EPA's Stormwater Program and state-specific stormwater management manuals. By proactively identifying potential problem areas, inspectors can recommend appropriate best management practices, BMP, during the planning stages, which is the most cost-effective and environmentally sound approach. This aligns with the ethical responsibility of the inspector to protect water quality and prevent pollution. An incorrect approach that relies solely on visual inspection of existing vegetation, without considering underlying soil conditions or drainage patterns, is professionally deficient. This failure to conduct a comprehensive assessment can lead to an underestimation of erosion potential, particularly in areas with permeable soils or subtle changes in slope that are not immediately apparent. This oversight constitutes a regulatory failure because it deviates from the requirement to identify all potential sources of sediment pollution. Ethically, it represents a dereliction of duty to adequately protect the environment. Another incorrect approach that focuses only on areas with steep slopes, while important, is incomplete. This overlooks potential erosion issues on gentler slopes where soil type, lack of vegetative cover, or concentrated flow paths can still lead to significant sediment transport. This is a regulatory failure as it fails to consider all contributing factors to erosion and sediment runoff as required by stormwater regulations. It is also an ethical failure as it prioritizes convenience over thoroughness, potentially leading to environmental harm. A third incorrect approach that prioritizes areas with the most visible existing erosion without considering the impact of future construction is also flawed. While existing erosion is a concern, the primary focus of pre-construction planning is to anticipate and mitigate erosion caused by the construction activities. Ignoring the potential for new or exacerbated erosion due to land disturbance is a significant regulatory and ethical failure. It demonstrates a lack of foresight and an incomplete understanding of the inspector's role in preventing pollution from construction sites. The professional decision-making process for similar situations should involve a multifaceted approach. 1. Understand the project scope and proposed land-disturbing activities. 2. Conduct a detailed site reconnaissance, paying attention to topography, drainage patterns, soil types, and existing vegetative cover. 3. Utilize available resources such as soil surveys, topographic maps, and aerial imagery to supplement field observations. 4. Critically evaluate how proposed activities will alter natural drainage and potentially destabilize soil. 5. Document all findings thoroughly, noting potential erosion and sediment sources and recommending appropriate BMPs for each. 6. Communicate findings clearly to the project team to ensure effective implementation of control measures. Question 14. What factors determine the most appropriate selection of erosion, sediment, and stormwater control best management practices, BMP, for a given construction site, ensuring compliance with regulatory requirements and effective environmental protection? Option A. The site-specific soil types, topography, rainfall patterns, the intended lifespan of the BMP, its documented effectiveness in similar conditions, and the applicable federal, state, and local stormwater regulations. Option B. the BMPs that are listed in a generic stormwater manual without considering the unique physical characteristics of the site or the specific performance criteria mandated by local authorities. Option C, the BMPs that are most familiar to the construction crew and can be installed with minimal effort or specialized equipment, without a thorough evaluation of their performance against regulatory standards. Option D, the lowest upfront cost of installation for any BMP that is commonly used in the region, regardless of its suitability for the specific site conditions or long-term maintenance needs. Correct answer is A. The site-specific soil types, topography, rainfall patterns, the intended lifespan of the BMP, its documented effectiveness in similar conditions, and the applicable federal, state, and local stormwater regulations. Explanation: this scenario is professionally challenging because selecting the appropriate best management practice, BMP, for erosion, sediment, and stormwater control requires a nuanced understanding of multiple, often competing factors. A certified erosion, sediment, and stormwater inspector must balance environmental protection with practical site constraints and economic realities, all while adhering strictly to regulatory mandates. The effectiveness of a BMP is not universal. It is highly dependent on specific site conditions, making a one-size-fits-all approach inappropriate and potentially non-compliant. The correct approach represents best professional practice because it prioritizes a comprehensive evaluation that integrates all critical elements mandated by regulatory frameworks, such as the U.S. EPA's Stormwater Program guidance and state-specific stormwater management manuals. This approach ensures that the chosen BMP is not only effective in controlling erosion and sediment, but also feasible given the site's topography, soil type, and available space. Furthermore, it considers the cost-effectiveness of the BMP in relation to its expected lifespan and maintenance requirements, and crucially, it aligns with the specific performance standards and design criteria outlined in the applicable regulations. This holistic evaluation minimizes the risk of noncompliance, reduces the likelihood of environmental damage, and promotes sustainable stormwater management. An incorrect approach that solely focuses on cost would be a regulatory failure, because it disregards the primary objective of erosion and sediment control, which is to protect water quality and aquatic habitats as required by the Clean Water Act and associated state regulations. Such an approach could lead to the selection of an ineffective BMP, resulting in ongoing pollution and potential enforcement actions. An approach that prioritizes only the perceived ease of installation would be an ethical and regulatory failure, because it overlooks the critical aspect of long-term effectiveness and maintenance, potentially leading to BMP failure and subsequent environmental harm, violating the inspector's duty to ensure compliance and protect public resources. An approach that exclusively considers the most commonly used BMPs without assessing site-specific suitability would be a professional failure, as it demonstrates a lack of due diligence and an abdication of the inspector's responsibility to apply best professional judgment tailored to the unique conditions of the project, potentially leading to noncompliance with performance standards. Professionals should employ a decision-making framework that begins with a thorough site assessment, identifying all relevant physical characteristics and potential constraints. This is followed by a review of the specific regulatory requirements and performance standards applicable to the project. Next, a range of potential BMPs should be identified, and each should be evaluated against the site conditions, their documented effectiveness for similar scenarios, their installation and maintenance costs, and their compliance with regulatory criteria. The BMP that best satisfies all these criteria, with a strong emphasis on regulatory compliance and environmental protection, should be selected. This iterative process ensures a defensible and effective stormwater management plan. Question 15. When evaluating the peak runoff for a phased commercial development project that will significantly alter the site's imperviousness over several years, which approach to runoff calculation best aligns with regulatory expectations for ensuring adequate stormwater control design? Option A. Relying solely on a general rainfall intensity duration frequency curve without considering the specific site's drainage characteristics or the impact of phased development. Option B. Employing a simplified empirical formula based on average annual rainfall without accounting for peak storm events or the site's specific hydrologic response. Option C. Utilizing a hydrological modeling software that can simulate runoff based on varying rainfall events changing site conditions across development phases, and incorporating site-specific soil and land cover data. Option D, consistently applying the rational method throughout all phases of development, assuming a constant time of concentration and rainfall intensity for the entire project duration. Correct answer is D, consistently applying the rational method throughout all phases of development, assuming a constant time of concentration and rainfall intensity for the entire project duration. Explanation: this scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors, selecting the most appropriate method for estimating peak runoff from a developing site. The challenge lies in balancing accuracy, data availability, and regulatory requirements. A developing site, by its nature, has changing imperviousness and drainage characteristics, making a static calculation method potentially less reliable over time. The inspector must consider the stage of development and the specific requirements of the local stormwater management regulations. The correct approach involves understanding the limitations and applicability of different runoff calculation methods as defined by the relevant U.S. EPA guidelines and state-specific stormwater management manuals, which are the governing frameworks for this exam. The rational method is often suitable for smaller, relatively homogeneous drainage areas, but its assumptions can become strained with larger or more complex sites, especially those undergoing phased development where runoff characteristics are dynamic. Utilizing a more sophisticated method, such as a hydrological model that can account for varying rainfall intensities, time of concentration changes due to development phases, and antecedent moisture conditions, is often preferred for larger or more complex sites, or when regulatory requirements mandate it for certain project types or sizes. This ensures a more accurate and defensible peak flow estimate, which is critical for designing effective stormwater controls that meet permit requirements and protect water quality. An incorrect approach would be to rigidly apply the rational method to a large, complex, or rapidly developing site without considering its limitations or specific regulatory guidance. This fails to acknowledge that the method's assumptions may not hold, leading to potentially inaccurate peak flow estimates. Such an approach could result in undersized or oversized stormwater controls, both of which are problematic. Undersized controls fail to meet regulatory performance standards, increasing the risk of pollutant discharge and potential enforcement actions. Oversized controls represent an inefficient use of resources and can sometimes create unintended hydrological consequences. Another incorrect approach would be to solely rely on historical rainfall data without adjusting for future climate projections or site-specific conditions, as this ignores the dynamic nature of stormwater management and the need for resilient design. Professionals should approach this by first identifying the specific regulatory requirements for runoff calculations within their jurisdiction. This includes understanding the applicability thresholds for different methods based on drainage area size, project type, and the stage of development. They should then assess the site's characteristics, including size, topography, soil types, and the planned sequence of development. Based on this assessment and regulatory guidance, they can then select the most appropriate calculation method. If the rational method is permitted and appropriate for the site's scale and complexity, it can be used. However, for larger, more complex or phased developments, or when regulations require it, a more advanced hydrological modeling approach should be employed. This systematic process ensures compliance, promotes effective stormwater management, and upholds professional responsibility. Question 16. The control framework reveals that a certified erosion, sediment, and stormwater inspector must assess soil conditions to ensure the effectiveness of best management practices, BMP. During an inspection of a construction site, the inspector observes soil exhibiting distinct, vertically oriented columns with flat, angular tops. This structure is known to be prone to surface sealing when wet and can limit infiltration. Considering the inspector's responsibilities under the regulatory framework, which of the following actions best demonstrates a thorough understanding of soil structure's impact on stormwater management? Option A, focusing on the visual appearance of the soil structure without considering its hydrological properties or how it might affect BMP performance. Option B, recommending a change in BMPs solely based on the visual identification of the soil structure, without a detailed assessment of site-specific conditions and regulatory requirements. Option C, noting the soil structure as prismatic and moving on to inspect other site features, assuming the installed erosion controls are adequate. Option D. Documenting the observed soil structure and evaluating its potential impact on runoff and infiltration, then verifying if the installed BMPs are appropriate for these conditions and are functioning as intended. The correct answer is D. Documenting the observed soil structure and evaluating its potential impact on runoff and infiltration, then verifying if the installed BMPs are appropriate for these conditions and are functioning as intended. Explanation. This scenario is professionally challenging because the inspector must apply knowledge of soil structure to a practical, on-site situation, directly impacting the effectiveness of erosion and sediment control measures. The inspector's judgment is critical in determining if existing conditions meet regulatory standards for stormwater management. The correct approach represents best professional practice because it directly aligns with the fundamental principles of soil science and their application within the regulatory framework for erosion and sediment control. Understanding how soil structure influences infiltration, runoff, and erodibility is essential for selecting and verifying the efficacy of best management practices, BMP, specifically recognizing granular soil's tendency to drain quickly and resist compaction, peaty soil's potential for surface sealing and reduced infiltration, blocky soil's moderate drainage and stability, and prismatic soil's susceptibility to frost heave and slaking, allows for informed decisions about BMP selection and maintenance. This approach ensures compliance with regulations that mandate effective stormwater management to protect water quality and prevent off-site impacts. An incorrect approach that focuses solely on visual identification without considering the implications for stormwater management is professionally unacceptable. This fails to meet the core objective of the inspector's role, which is to ensure that erosion and sediment control measures are adequate to prevent pollution. For example, simply noting a soil structure type without assessing its impact on runoff velocity or infiltration rates means the inspector is not fulfilling their duty to evaluate the effectiveness of control measures. Another incorrect approach that prioritizes ease of inspection over regulatory requirements is also professionally flawed. The inspector's primary obligation is to uphold the regulatory framework, not to simplify their task at the expense of compliance. This could lead to overlooking critical issues that pose a risk to water quality. A third incorrect approach that relies on anecdotal evidence or personal experience without grounding it in the established principles of soil science and regulatory guidance is ethically and professionally unsound. This introduces subjectivity and potential bias, undermining the objective assessment required for regulatory compliance. The professional decision-making process for similar situations should involve a systematic evaluation. First, identify the soil structure present. Second, understand the hydrological implications of that specific structure, e.g., infiltration rates, susceptibility to erosion. Third, assess how these implications affect the performance of existing or proposed BMPs. And finally, determine if the current conditions and controls meet the specific requirements of the applicable regulatory framework. This structured approach ensures that decisions are data-driven, scientifically sound, and compliant with legal and ethical obligations. Question 17. Risk assessment procedures indicate that sediment deposition is occurring in a downstream channel adjacent to a construction site. Which of the following approaches best reflects the professional responsibilities of a certified erosion, sediment, and stormwater inspector in assessing the cause and extent of this deposition? Option A. Systematically evaluate the installation, condition, and performance of all site best management practices, BMP, in relation to stormwater runoff patterns and the observed sediment deposition, correlating findings with the project's Stormwater Pollution Prevention Plan, SWPPP. Option B. Assume that the construction site is the sole source of the observed sediment deposition and recommend immediate and extensive remediation measures without a detailed assessment of individual BMP effectiveness. Option C. Focus solely on the presence of any visible sediment in the downstream channel as definitive proof of BMP failure, without further investigation into the specific BMPs or site conditions. Option D. Attribute all observed sediment deposition to natural geological processes and background sediment loads in the receiving water body, assuming no direct link to the construction activities. The correct answer is A. Systematically evaluate the installation, condition, and performance of all site best management practices, BMP, in relation to stormwater runoff patterns and the observed sediment deposition, correlating findings with the project's Stormwater Pollution Prevention Plan, SWPPP. Explanation. This scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors, evaluating the effectiveness of sediment transport and deposition control measures in a dynamic environment. The challenge lies in discerning whether observed deposition is a natural occurrence or a direct consequence of inadequate or improperly implemented best management practices, BMP. Accurate assessment is critical for ensuring compliance with regulatory requirements designed to protect water quality and aquatic habitats. The correct approach involves a systematic evaluation that directly links observed deposition to the performance of specific BMPs and the site's overall stormwater management plan. This aligns with the core responsibilities of an inspector, which include verifying that BMPs are installed correctly, maintained adequately, and functioning as intended to minimize sediment runoff. Regulatory frameworks, such as the U.S. EPA's Stormwater Management Program, Guidance, and State-Specific Stormwater Pollution Prevention Plans, SWPPP, mandate that inspectors assess the effectiveness of controls and require corrective actions when deficiencies are identified. This approach represents best professional practice because it is data-driven, evidence-based, and directly addresses the regulatory intent of preventing sediment pollution. An incorrect approach would be to attribute all observed deposition solely to natural geological processes without a thorough investigation of site conditions and BMP performance. This fails to acknowledge the inspector's duty to identify and address human-induced impacts on water quality. Ethically, it represents a dereliction of duty to overlook potential noncompliance. Regulatory failure occurs because it bypasses the requirement to ensure that the project is minimizing sediment discharge as stipulated in permits and plans. Another incorrect approach is to focus solely on the presence of sediment without considering the context of the site's construction phase and the intended function of the BMPs. This overlooks the fact that some sediment generation is inherent in construction, and the goal of BMPs is to manage, not eliminate, this generation. Regulatory failure arises from an incomplete understanding of the permit requirements, which typically focus on the control of sediment, not its complete absence. Ethically, this approach can lead to unnecessary enforcement actions or, conversely, a failure to enforce when necessary. A third incorrect approach is to assume that any visible sediment in receiving waters automatically signifies a failure of the project's BMPs, regardless of the distance from the site or the presence of other potential sources. This can lead to misdirected enforcement and an inaccurate assessment of the project's impact. Regulatory failure occurs when enforcement is based on assumption rather than direct evidence linking the observed deposition to the specific construction site and its stormwater management system. Ethically, it is unprofessional to make definitive judgments without sufficient investigation. The professional decision-making process for similar situations should involve 1. Understanding the project's SWPPP and permit requirements. 2. Visually inspecting the site and surrounding areas for evidence of erosion and sediment tracking. 3. Evaluating the installation and condition of all installed BMPs. 4. Observing the flow of stormwater and identifying potential pathways for sediment transport. 5. Correlating observed sediment deposition with the performance of specific BMPs and the overall site management. 6. Documenting findings with clear evidence, including photographs and notes, to support conclusions regarding compliance or noncompliance. Question 18. The efficiency study reveals that a construction site is experiencing significant sediment runoff into a nearby waterway, despite the presence of several erosion and sediment control measures. The inspector observes that following moderate rainfall events, large volumes of water are visibly flowing off the site, carrying substantial amounts of sediment. There is minimal evidence of ponding or significant soil saturation in the vegetated areas, and the ground surface in disturbed areas appears largely impermeable to water penetration. The inspector must determine the primary hydrologic process contributing to the observed sediment transport. Option A. The high volume and velocity of surface runoff, driven by limited infiltration and evapotranspiration, is the primary contributor to sediment transport. Option B. The primary issue is the high rate of precipitation exceeding the site's design capacity for infiltration, with runoff being a secondary consequence. Option C. Evapotranspiration rates are exceptionally low, leading to increased soil moisture and subsequent sediment mobilization, despite minimal visible runoff. Option D. The theoretical infiltration capacity of the soil, which is assumed to be high, is preventing significant runoff and thus is not the cause of sediment transport. The correct answer is A. The high volume and velocity of surface runoff, driven by limited infiltration and evapotranspiration, is the primary contributor to sediment transport. Explanation: this scenario is professionally challenging because it requires an inspector to interpret complex hydrologic processes in the context of regulatory compliance without direct measurement of all components. The inspector must rely on observable evidence and understanding of how precipitation, infiltration, runoff, and evapotranspiration interact to assess the effectiveness of erosion and sediment control measures. The challenge lies in inferring the performance of BMPs based on their impact on runoff and sediment transport, even when direct measurement of infiltration rates or evapotranspiration volumes is not feasible. The correct approach represents best professional practice because it directly addresses the observable outcomes of the hydrologic cycle as they relate to erosion and sediment control. By focusing on the volume and velocity of runoff, the presence of sediment deposition, and the condition of vegetation, indicating evapotranspiration and infiltration, the inspector is evaluating the direct impact of the site's activities on water movement and soil stability. This aligns with the core mandate of the certified erosion, sediment, and stormwater inspector role, which is to ensure compliance with regulations designed to prevent pollution from stormwater runoff. The inspector's judgment is grounded in the physical evidence of the hydrologic processes at play and their consequences. An incorrect approach that focuses solely on the theoretical aspects of the hydrologic cycle without correlating them to site conditions or BMP performance would be a regulatory failure. For example, simply stating that precipitation will eventually infiltrate without observing evidence of infiltration, e.g., saturated soils, ponding, or its impact on runoff would be insufficient. Similarly, ignoring the visible signs of excessive runoff and sediment transport because the theoretical infiltration rate is assumed to be high would be a failure to identify noncompliance. Ethically, an inspector has a duty to accurately assess site conditions and their compliance with regulations, not to rely on assumptions that may mask underlying problems. Professionals should use a decision-making framework that begins with understanding the regulatory requirements for the specific project and jurisdiction. This is followed by a site inspection that systematically observes the physical manifestations of the hydrologic cycle, evidence of precipitation impact, signs of infiltration, or lack thereof, the volume, velocity, and path of runoff, and the presence and extent of sediment transport and deposition. The inspector then evaluates how these observed hydrologic processes are being managed by the installed best management practices, BMP. If the observed outcomes indicate a failure of the BMPs to control erosion and sediment, the inspector must document these findings and recommend corrective actions, referencing the specific regulatory provisions that are being violated. This iterative process of observation, evaluation against regulations, and documentation is crucial. Question 19. The audit findings indicate that while an erosion and sediment control plan (ESC) has been developed and approved, and some best management practices (BMP) are present on site, there are significant concerns regarding the plan's overall effectiveness in preventing sediment runoff. Given this situation, which of the following approaches best addresses the inspector's responsibility to ensure compliance with the ESC objectives and regulatory requirements? Option A. Focus solely on the contractor's documentation of BMP installation and reported progress, accepting their records as proof of compliance without independent verification of site conditions or BMP effectiveness. Option B. Review the ESC objectives and the implementation schedule, and if the schedule has not been strictly adhered to, recommend immediate cessation of all site activities until the original schedule can be met. Option C. Conduct a detailed site inspection to verify the proper installation and maintenance of all BMPs, assess their effectiveness in controlling erosion and sediment based on current site conditions, and compare the actual implementation progress against the ESC schedule, identifying any deviations and their potential impact. Option D. Immediately issue a notice of violation based on the audit findings, assuming the ESC is inherently flawed and its implementation has failed, without further site-specific investigation. The correct answer is C. Conduct a detailed site inspection to verify the proper installation and maintenance of all BMPs, assess their effectiveness in controlling erosion and sediment based on current site conditions, and compare the actual implementation progress against the ESP schedule, identifying any deviations and their potential impact. Explanation. Scenario analysis. This scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors: a discrepancy between a developed erosion and sediment control plan ESP and the actual site conditions and implementation progress. The audit findings highlight a potential failure in the plan's effectiveness or its execution. The inspector must critically evaluate the ESP objectives, the suitability and proper installation of best management practices, BMP, and the adherence to the implementation schedule. This requires not just knowledge of regulations, but also practical site assessment skills and the ability to identify root causes of noncompliance. Correct approach analysis. The correct approach involves a thorough review of the ESP against current site conditions and the documented implementation schedule. This means verifying that the stated objectives of the ESP are still relevant and achievable given the project's phase and the observed site condition. It requires assessing whether the installed BMPs are appropriate for the identified erosion and sediment risks, and if they have been installed according to manufacturer specifications and regulatory guidance. Crucially, it involves determining if the implementation schedule has been followed, and if not, understanding the reasons for the delay and its impact on the ESP effectiveness. This comprehensive, on-the-ground assessment ensures that the ESP remains a functional and compliant document that effectively manages stormwater impacts. This aligns with the core responsibilities of an inspector to ensure compliance with applicable regulations, such as those outlined in the U.S. EPA's Stormwater Management Program or state-specific stormwater permits, which mandate effective ESP and their diligent implementation. Incorrect approach is analysis. One incorrect approach would be to solely rely on the documentation of the ESP and the contractor's reported progress without verifying actual site conditions. This fails to acknowledge that plans are dynamic documents that must be adapted to changing site realities. Ethically and regulatorily, this approach is deficient because it bypasses the inspector's duty to conduct site-specific evaluations and ensure that the plan is being implemented effectively in the field. It could lead to continued environmental degradation and non-compliance with permit conditions. Another incorrect approach would be to focus only on the installation of BMPs without considering the overall objectives of the ESP or the implementation schedule. While proper BMP installation is critical, if the BMPs are not addressing the primary erosion and sediment sources identified in the plan, or if they are installed significantly behind schedule, the ESP overall objectives will not be met. This approach is flawed because it lacks a holistic view of stormwater management and can result in a false sense of compliance. It neglects the regulatory requirement for a comprehensive plan that addresses all aspects of erosion and sediment control throughout the project lifecycle. A third incorrect approach would be to assume that any deviation from the implementation schedule automatically renders the ESP ineffective, without investigating the reasons for the deviation or its actual impact. While schedules are important, unforeseen circumstances can arise. Rigid adherence to this assumption without further investigation can lead to unnecessary enforcement actions or the imposition of corrective measures that may not be proportionate to the actual risk. The regulatory framework typically allows for some flexibility when deviations are justified and do not compromise environmental protection. Professional reasoning. When faced with audit findings that suggest a disconnect between an ESP and site reality, a certified erosion, sediment, and stormwater inspector should employ a systematic, evidence-based decision-making process. This begins with a thorough review of the ESP to understand its stated objectives and intended BMPs. This is followed by a detailed site inspection to assess current conditions, the effectiveness of installed BMPs, and the progress against the implementation schedule. The inspector must then compare these field observations with the ESP and relevant regulatory requirements. If discrepancies are found, the inspector should investigate the root causes, considering factors such as design adequacy, installation quality, maintenance, and adherence to the schedule. Based on this comprehensive assessment, the inspector can then determine the appropriate course of action, which may include requiring plan revisions, corrective actions for BMPs, or adjustments to the implementation schedule, always prioritizing environmental protection and regulatory compliance. Question 20. The risk matrix shows a moderate potential for sediment runoff due to steep slopes in the proposed construction area. Which of the following site characterization approaches best informs the selection of appropriate erosion and sediment control measures? Option A. Evaluating the soil's permeability and erodibility in conjunction with the steep slopes to determine the likelihood of soil detachment and transport. Option B. Prioritizing the identification of existing surface water bodies, as their proximity is the primary driver of sediment impact. Option C. Focusing solely on the visual density and health of existing vegetation, assuming it will adequately stabilize the soil on the slopes. Option D. Analyzing the overall watershed size to determine the volume of runoff, without detailed consideration of local soil conditions on the slopes. Correct answer is A. Evaluating the soil's permeability and erodibility in conjunction with the steep slopes to determine the likelihood of soil detachment and transport. Explanation. This scenario presents a common challenge for certified erosion, sediment, and stormwater inspectors. Interpreting complex site conditions to predict potential impacts and select appropriate best management practices, BMP. The challenge lies in synthesizing information from topography, soil types, existing vegetation, and drainage patterns to anticipate how stormwater will behave during and after construction. A thorough understanding of these interconnected elements is crucial for effective site characterization, which forms the foundation of any successful stormwater pollution prevention plan, SWPPP. The correct approach represents best professional practice because it involves a systematic and comprehensive evaluation of all relevant site characteristics. This aligns with the fundamental principles of stormwater management and the inspector's role in ensuring compliance with regulatory frameworks. By considering how each factor influences runoff velocity, infiltration rates, and sediment transport potential, the inspector can accurately identify areas of high risk and select the most effective BMPs to mitigate those risks. This proactive and integrated assessment is essential for preventing sediment and pollutant discharges into waters of the United States, as mandated by federal regulations such as the Clean Water Act and associated EPA guidance. An incorrect approach that focuses solely on topography without considering soil type would be a regulatory failure. Topography dictates the slope and flow paths, but soil characteristics e.g., permeability, erodibility, significantly influence how water infiltrates and how easily soil particles are detached and transported. Ignoring soil type can lead to an underestimation of erosion potential and the selection of inadequate BMPs. Similarly, an approach that prioritizes existing vegetation as a sole indicator of stability without assessing its density, health, and the underlying soil conditions would be a failure. Healthy, dense vegetation can stabilize soil, but sparse or unhealthy vegetation, or vegetation on highly erodible soils, may not provide sufficient protection. An approach that only considers the immediate drainage patterns without projecting how construction activities will alter them is also a failure. Construction inherently changes drainage, and failing to anticipate these changes can lead to unexpected and significant erosion and sediment runoff. Ethically, inspectors have a duty to protect water quality, and these incomplete assessments would violate that duty by failing to adequately identify and address potential pollution sources. Professional decision-making in such situations requires a structured approach. 1. Gather all available data. Collect topographic maps, soil surveys, aerial imagery, and conduct thorough on-site observations. 2. Analyze interrelationships. Understand how topography influences flow, how soil type affects infiltration and erosion, how vegetation impacts soil stability, and how all these factors interact to create drainage patterns. 3. Predict potential impacts. Based on the analysis, anticipate where concentrated flows will occur, which areas are most susceptible to erosion, and what pollutants might be mobilized. 4. Select appropriate BMPs. Choose BMPs that directly address the identified risks and are suited to the site's specific characteristics. 5. Document findings and recommendations. Clearly record the site characterization and the rationale for BMP selection in the SWPPP.